All right, the purpose of this quick video is to help you with question number 4. What is the charge on the iron 3 complex ion in FeOH2 H2O4 Br? So there's a few things going on in this problem. One is this idea of what a complex ion is. So far you've likely seen ions that just have one single element, something like H+. You know H+ is an ion because it carries a charge. A hydrogen lost one electron to get a charge of +1. Well, it turns out ions can also be made of multiple atoms. Ions can also be made of multiple atoms. In the case of a complex ion, you have a metal. In this case, we have Fe, or iron. I'm just going to refer to it as Fe because I think saying iron and ion gets a little confusing, so we'll just call it Fe. Fe has a charge of 3+. How do I know that? Because this Fe3 indicates that there's a charge of 3+. The Roman numerals actually tell me the charge. This is necessary for my transition metals because my transition metals can have what's called variable oxidation states, which hopefully you saw in the chapter. So in my complex ion, I have Fe3+ surrounded by some OHs, 2 OHs specifically, and 4 H2Os, all attracted to each other with electrostatic attractions, and this entire thing carries a charge because it is an ion. All of this together that's within the circle that I have here is the complex ion. What they're asking me for is what is the charge in total of all of these atoms together. So the complex ion, that's the part that's within these brackets here. And then the Br is associated with the complex ion, is attracted to the complex ion, and all together they form a connection. But the actual ion, the part that they're asking us about, is in the brackets here. All right, so how do I go about figuring out the charge on the complex ion here? There's a couple things to think about, or there's a couple ways to do it. The first one that I want to point out is we can use the charges that all of these elements would be likely to form. We know the charge of 3+, and we can put all of the atoms together. All right, so what do I mean by that? How do I know the charges that O and H would be likely to form? Well, that actually gets at what an oxidation state is. I know you probably haven't seen that word before, but you have definitely dealt with this idea. So, just as a reminder, I'm going to fill in the valence electrons for all of my main group elements. Based on those valence electrons, I can also predict the charge that is most likely to form in each of these main group elements. This was likely something that you did last year. So, for group 1 elements, they have one valence electron. They are most likely to get a full energy level, just going to lose this one valence electron. When they lose valence electrons, they'll form a charge of +1. So everyone in group 1, the most likely charge that any of these elements would carry would be +1. Same idea here, that everyone in group 2, if they need to form some kind of connection, they're most likely to give up 2 electrons and carry a charge of +2. Same idea here. Now, if I have 4 electrons in my outer energy level, I could either lose those 4 electrons and gain a charge of +4, or I could gain 4 electrons and gain a charge of -4. If I have 5 electrons in my outer energy level, and notice we're only talking about S and P energy levels here. If I have 5 electrons in my outer energy level, well, to get to 8 electrons total, I am more likely to gain 3 electrons than I would be to lose all 5 of my valence electrons. So if I gain 3 electrons to get to my full 8, then I would gain a charge of -3. For 6 valence electrons, I would likely gain 2 electrons instead of losing all 6 of those. If I gain 2 electrons, I get a charge of -2. And here, if I gain 1 electron to get to a full outer shell of 8, then I would carry a charge of -1. So these are all of the most likely charges to occur for all of these elements. Now I know that these elements don't all form ionic bonds, right? Sometimes they don't carry a full charge. If I had a molecule like CH4, for example, well, that's a covalent bond that forms between the C and the H. So the H does not carry a full +1 charge. The C does not carry a full -4 charge. But for oxidation states, that's how we assign them. We assume that instead of sharing the electrons, it is actually a full charge that forms there. And so these would be the oxidation states for each of these elements, or at least the most likely oxidation states to form for each of these elements in the main group. All right, so I can just go ahead and basically add these up in order to figure out my oxidation states here. I'm going to move to a new page to make this a little bit clearer. And I'm going to get this picture. Perfect. All right. So let's actually just make this nice and big so we can work. All right. And not crooked. There we go. All right. So again, we're looking at this ion in brackets. In this case, I know Fe has a charge of +3. Why do I know that? Fe can carry different charges, true, but remember they told us it's iron 3, or Fe3. So those Roman numerals tell me +3. Awesome. Oxygen, most likely oxidation state for oxygen, -2. Most likely oxidation state for hydrogen, +1. So together, each OH should carry a charge of -1. There's 2 of them in total, so this entire OH2 should have a charge of -2. So I'm just adding up the oxidation states for each atom that's present. So oxygen has an oxidation state of -2, or would the most likely charge that it would carry, -2. Hydrogen +1, so OH altogether is -1. There's 2 OHs, so -2. Water, -2. Hydrogen, each one is +1, so in total, 2 hydrogens is +2, and so water, of course, does not have any charge, and so we don't need to consider these in the charge. And so if I have -3 +2, my charge should be +1. All right. The other way that I can see that is I know bromine should carry a -1 charge. So that means even if I don't do any of this math here, bromine should carry a -1 charge. So that tells me that in order for this to form a molecule, or in order for this entire thing to not have a charge, and I know that it doesn't because there's no charge listed after the bromine, so in order for the whole thing that they've shown us here to not have a charge, then this ion, this entire ion in brackets, would actually have to have a +1 charge. All right, hope that helps. Bye for now.